introduction. Welcome for the second part of the training on numerical computing with Rust on CPU. As you know, during the first part, we have a really nice introduction on Rust. Now you are going to have access to the second part with numerical simulation on Rust. This training is co-organized by NCC France and of course NCC Slovakia. So thanks a lot for Lucia and also Michal and all the team. As you know, I'm Karim Azoum from the French NCC. If you need some help or some question, just send us a mail to Karim Azoum or Marie-Lande Pensmer. We are here to support you. And of course, as you know, this training is realized by the participation of IGC Lab, the National Supercomputing Center of Slovakia, and Sonar Lake. And now I'm going to give the floor to Adrien Graland, which is the software developer at IGC Lab, a French laboratory attached to CNRS and Paris-Saclay and Paris Cité universities. If you are ready, Adrien, you can take the floor.
Sure. I'm not sure if I can share on top of your slide, but yeah, okay, then I can do it. So welcome to this second day. Let me maybe take a quick tour of what we did so far. So yesterday I started with some motivation as for what are the main qualities of Rust, its main competition, and why we would use it instead of C++, which is the language that's most similar to it in the current HPC ecosystem. We went through some environment setup process. I know it was rough for some of you. I apologize for that. That's one of the difficult parts of online trainings. I try my best to help you, but anyway, if you still get some issues, please get in touch and let's see if we can fix them today at last. We went through some first Rust elements, like we discussed, how we can print stuff in the console, define variables. We discussed type inference and how it works and why it's common in Rust. We went into a bit more details on the console output facilities, the debug output, which is very convenient when, as you know, debugging. And we discussed a bit assertions, which we use in this course also as a way to check that your solutions to the exercises are correct. Then we went into the primitive number types of Rust and some others that may get into the future. We saw that overall it's quite similar to the logic of numbers in C and C++. However, there are a few major differences. In particular, there are no implicit conversions. Is it better that way as far as the browser window is concerned? Okay. Then we studied arithmetic, so that much like we don't have implicit conversion, we don't have mixed arithmetic. We saw that number types have methods. And then we went on to study the third main component of numerical programs, which is iteration, loops, and arrays. So we saw that we can iterate over ranges of integers, as in many other programming languages, with a syntax that exhibits a slight preference towards left inclusive, right exclusive ranges, as in Python. But if you want inclusive ranges, we have them as well. We saw how iterators are central parts of loops in Rust, and we saw that they are more powerful than the cousins of iterators that you can see in C++, for example. They are closer to C++ 20 ranges. except they get some very convenient chained method syntax, which allows you to iteratively build a relatively complex iterator that does arbitrarily difficult iteration patterns. Then we studied our two main types for storing collections of numbers, arrays and vectors. We saw that arrays are located on the stack, more precisely they are located in line. Inside of the, if you put them inside of a struct that's allocated on the heap, they will obviously be allocated on the heap, but you will have only one heap allocation and not two. We contrasted that to vectors, which are located on the heap always, using the Rust equivalent of malloc and free. We saw that overall arrays are a bit more of a special case than vectors, and most of the time, if you don't know, you should probably be using vectors. We saw that there are two basic syntaxes for declaring arrays, one where you list all the elements and one where you repeat a single element. We also get, for more complicated cases, the array from FN standard library. And even though the first two have equivalents for vector via the vec macro, the third one doesn't have an equivalent because we get something a lot more powerful in Rust, which is that any iterator pipeline can instead be collected into a collection. This includes vectors, but also other standard library collections that we will not be studying in this course, like hash maps and so on. We saw that arrays and vectors can be iterated over. And we saw that they have some indexing operations, which unlike in C and C++, do not exhibit undefined behavior when an invalid index is used. Instead, there is a check that will lead to program termination through a process called panicking. We saw that even if this is much preferable from the point of view of program correctness, security, and debugging, because undefined behavior can be quite a pain to debug, it's still not super idle from the point of view of performance, because if you do these indexing checks in a loop, they can easily turn out to be quite expensive. Which is why normally you will want to do most of your iterations using iterators. We saw that there is a special kind of indexing called slicing, which allows you to extract, let's say, part of an array or a vector into a slice object that behaves as if you had an array containing only a subset of the element, except it's not a copy, it's like a reference to the original. And since slicing like that has the same drawbacks of indexing in terms of runtime checking and performance, we saw that common slicing scenarios are also covered via iterators. Today, I would like to start by going a bit more through some of the chapters, assuming that some of you already had the time to go through them. First, I would like to go through the next chapter where we start now taking collections of numbers and squaring them, computing the square of them. And to do that, we are going to need a new Rust concept that we have not seen so far, which is anonymous functions, also known as lambdas in programming language theory circles. So the general idea of a lambda is this. In Rust, you could define functions anywhere, including inside of other functions. That's a more general design choice of this language. You can define types inside of functions. You can define types inside of expressions, even if you want to. You can declare almost anything, almost anywhere. But Rust is not Python. When you declare a function, you do not have access to variables from the outer scope. So even if this code, which it just declares a function with two parameters a and b and sums them, is legal, this one is not, because here we are accessing parameters x and y from the function declared in the outer scope, and that's illegal. To handle this sort of thing, this sort of needs, Rust gives you lambda functions. anonymous functions. So the way they work is that you can assign to a variable or just pass as a parameter to a function some a bit weird syntax in the beginning, which is composed of a pair of pipe characters between which you can write parameter declarations as for functions. This works like a very concise version of a function declaration, but you get a few extra expressive power features. First of all, you can access values from the outer scope inside of these anonymous functions. Second, you get more type inferences. You can see that the type, the return type is inferred. And if you have parameters, you can also let their type be inferred. Like if you see the example below where I show that you can spell out the types, I could instead have written pipe A, comma B, pipe, and the compiler would have accepted that as well. And by that point, you may be wondering, yeah, but why do we need to define functions like these that access environment and so on? The main use in Rust is interaction with something called higher order functions, which is functions that take other functions as inputs or return other functions as outputs. Before I can introduce those, so I need to introduce another Rust theoretical concept, which is traits. This is a relatively short course, and we will not have the time to fully cover what Rust traits are able to do. But in a nutshell, they are a very general polymorphism feature that allow you to associate a number of data, operation, type declarations with individual types in your program. Like, for example, the add trait is used to overload the plus operator in Rust. And you can define implementations of the add traits for any struct you define, and then you can use this struct with the plus operator. Traits are very flexible. They can be used to replace any of the polymorphism features of C++, virtual methods, overrides, templates, concepts, type traits, functions, and method overloading, implicit conversion, you name it. And that's a bit of a double-edged sword. On one hand, it means that traits are a lot easier to use than the mixture of all these polymorphism features of C++, because you don't need to constantly think about all the way the different features interact. You just have one polymorphism feature. The flip side of this coin, however, is that traits are a bit of a complex feature to learn. Thankfully, its basic use of traits is easy. Here, involving one particular trait called fn, which represents something that can be called like a function for certain parameters, and that will return if called a result of a certain type. The fn trait is currently handled a bit specially by the compiler, which allows it to have some special syntax. So here you see that I can define a function that a callable that takes a 16-bit signed integer and a 32-bit floating point number and returns a usize using this trait. Any function or closure or anonymous function, sorry, that can be called that way will implement this trait. And then inside of my code, what I can do is I can say, no, okay, I'm taking such a function as a parameter, and then I call it and I display the result. And the syntax for this is instead of saying my parameter has type this or that, you say my function can take as a parameter any type that can be called like a function for these parameters and this result type, which means that I can use it either with regular functions or with anonymous functions. And here maybe you can start to see the usefulness, but the main idea is that these are extremely powerful for use cases like transforming iterators, where you want to turn values from the iterator into different ones, or for use cases like querying a collection, like maybe you want to find all elements of a collection that match some condition. And another feature that we will not use as much in this course, but I wanted to point out for symmetry, is that you can also return from a function this infiltrate syntax. And in this case, it means something a little different. Here, using the infiltrate syntax allowed our function to accept many types as input, anything that can be called like a function with these parameters. Whereas here, instead, using infiltrate like that allows us to be less specific about the return type of our function. It means that we can say we can return any function that can be called with those parameters and return this result. And this means that later on we can change what this function, what type this function returns. We can return a normal function like declared above. And the caller code will still work because with this syntax, we have not allowed callers to care about which specific type is returned by this function. We only tell them, I'm going to return a type, and that type can be called like a function, and that's all you need to know. So back to our numerical computing concerns now. These higher order functions can be used in an iteration context to transform elements of an iterator. And by that I mean that if I have some object that can be iterated over, like an array, for example, and I iterate over it, and then I call some iterator adapter called map, and I give it as a parameter a function that takes one element from an iterator and produces a different value, then what I will get is an iterator that produces those values. Like in this case, I went from an iterator that produces elements from this array to an iterator that produces the square of elements from this array. And then, you know, that's an iterator like all other iterators, so I can just collect it into a vector. And then I will end up with a vector that contains the square of all elements. And the powerful side of it is that this is designed in such a way that writing this sort of pipeline is as efficient as writing a loop over one element that one array that writes into another array. In fact, it will usually be more efficient because iterative constructions of vector with push may run into some compiler optimizer corner cases. But let's not get into this for now. So now, okay, we can compute the square of an array of numbers. That's good. What else can we do? Well, let's take this iterator concept a bit further down the road now. And now let's try to take two different iterators and combine them. So in an earlier chapter, I mentioned that with the constructs I've shown so far, iterating over two different objects at the same time is a bit of a pain. Like if you have two vectors like this, well, you can iterate over one easily, but to iterate over both at the same time, the only tool you have so far is to generate the indices of individual elements with the enumerate adapter, and then use that to index into the second vector, which will result in all the usual issues of bound checking. But we can actually do better. there is another iterator adapter, which is called zip. And the way it works is that given an iterator, you can zip it with another iterator or iterable object like an array or vector. And what this will do is that you will get an iterator of tuples, pairs of elements, that for each iteration gives you one element from the first source and one element from the second source in a lockstep. So like this iteration pipeline will produce first the pair 1 and 5, first elements of the 2, then 2 and 6, second element of the 2, 3 and 7, and so on. Now, you may have used other programming languages like C++ and Python that have this zip feature before. And you may know that there are a couple of design questions that programming language designers must answer to make this work. The first question is, what should zip do when the two input iterators do not produce the same number of elements? And the second question that is particularly relevant to C++ practitioners is this as performant as a manual loop with bound checks removed? To the first question, the answer first is that we stop when the first of the two zipped iterators stops. This can be debated. There would have been other options. We could have done it the C++ way and exhibit undefined behavior in that case. We could have treated that as a usage error and stopped iteration with some error handling mechanism like a panic. I guess by now it's not a surprise to you that Rust does not pick the undefined behavior option. That's kind of against the design goals of the language. This one is more debatable. I think it might have been out of concern for how this could affect optimizer decisions and degrade the quality of generated code. But in any case, if you need this kind of behavior, you can easily implement it as a third-party library. And in fact, one is readily available. When it comes to runtime performance, here we get something quite different from C++20, where zip is as good as a hand-tuned indexing loop. It does not exhibit the runtime performance issues that you would get if you try to use the zip operations of C++20 ranges as implemented by GCC currently. And my understanding is that this happens because tuples are treated specially by the Rust compiler. They are not implemented as a library like in C++, and this allows the compiler to give its backend some extra help so that you have less chance of generating tuple structs on the stack, destroying other optimizations. Once we have this range zipping operation, what we can do is to implement another primitive from linear algebra called the Hadamard product. So in linear algebra, as you may know, we have many different products, dot products, cross products. The Hadamard product is another one of these. It's basically you take two vectors of same dimension, and you produce a vector of products of pairwise products of elements from the two inputs. And using zipping and mapping, this is just a matter of taking the first vector, zipping it with the second one, transforming the resulting iterator of pairs into an iterator of products, and finally collecting that into a new vector. However, you need here to bear in mind that the two inputs may not be of the same length, as mentioned earlier. Finally, the last chapter I wanted to cover with you this morning is the one about summing floats, because this is where performance will start to become a problem with naive use of iterators. So basically, we could, given an array of floating point numbers, compute their sum just by taking the array, iterating over it, and computing the sum of elements. That would work, but as we will see later, we will get some performance problems. There is one more immediate problem that we'll get before that, however, which is that here you need to specify the type of the sum, which is not usual. And the reason this happens is that Rust allows you to sum over both an iterator of numbers and an iterator of reference numbers. This was an attempt to make the operation more convenient, like when you're iterating over an array in place without destroying it, you can just operate over the iterator of references. But anytime you add generics in Rust, there is a price to pay, and the price to pay is loss of type inference, and that's what you see here. We can combine this sum reduction to get the classic dot product from linear algebra. We can, take one array, iterate over it, zip it with another array to iterate over that as well. We get pairs of elements, we multiply them, we sum. And then, you get your local performance expert yelling at you because you have been using sums of products and not fuse, multiply, add, which are faster on modern CPUs. That's okay. For this, you can use a more advanced reduction called fold. So here the idea is we start from our iterator of pairs again, but this time we do this operation where we specify the starting value of accumulator. So in our case, for dot product, we start at 0. And then we define each iteration step of the accumulation. We say, given a certain accumulator value on a new pair of elements, we produce the fuse, multiply, add equivalent of multiplying x by y and adding the former accumulator, and this will become our new accumulator. And basically what I'm saying here is that when you write this, you get the equivalent of this code. And again, that works, but the problem is that this code, from a performance point of view, is wrong. We will see in the next step how bad is it, and then you will be able to know that you're able to quantify the problem. We will see in subsequent chapters how we can solve it. So first, how can we measure the problem? So here we are going to need a benchmarking library called a criterion. This may not be forever be the case, but at the moment, the built-in the Rust compiler has some built-in benchmarking feature, but right now it's not generally available. It's only available in an experimental form on the nightly versions of the compiler, because the intent is to rework this feature before realizing it as part of the stable compiler. However, a subset of the API used by this built-in benchmarking harness is available today in stable versions of the compiler. And you can use this building block together with the criterion external library to easily build micro benchmarks. So first, we need to add criterion as a dependency, which is as easy as just running this command. And then, unfortunately, we need to muck a bit with the project's compilation configuration. So here, just to be clear, what we are doing is to disable the nightly only built-in benchmarking harness of the Rust compiler, because otherwise it will give us issues later on when we try to run our criterion benchmark and pass parameters to them over the command line. Once we've done this ugly thing, then we can create a benchmark file. We put a bit of boilerplate in there. And finally, we can start defining benchmarks. Like, for example, I define a benchmark called the square root of 4.2, which runs over a number of iterations. And for each iteration, it takes 4.2 as an input, runs it through some optimization barrier, and produces the square root of that. We need this optimization barrier because otherwise the compiler will see that we are just computing the square root of the same number over and over again. And it will use that to perform optimizations that are not right, like replacing the benchmarking loop with a single computation, or eliminating the part of the code of square roots that handles negative numbers, for example. So here I go a bit more into the details of that, and I invite you now to do this for yourself and see how bad it gets to just sum numbers using the sum method of iterators. So I see that we have a bunch of questions, so now I'm going to answer them. So where is the chat? It's here because sometimes there are some questions here as well. So everyone is using the Q&A today. That's perfect. So what is the difference between into iter and iter? So many objects can be turned into iterators. For some objects, like vectors, that's a destructive operation. Once you've turned a vector into an iterator, you cannot access the original vector anymore. Into iter is the destructive version of that. It tells you, take this value and turn it into an iterator, even if it means destroying the original value. This in turn allows some optimizations. Like, for example, if you have a vector of vector, you will be able to reuse the associated memory allocations when using into iter and not when using iter. Iter is method of arrays, vex, and slices in general, which instead does not consume the input array, but produces an iterator of references to the contents. I have not gotten yet into the nuances of this own value versus reference, because that's exactly the topic of the chapter right after the one I've just covered, called ownership. But basically, when you have a reference to an element, this allows you to access the input collection in place and to reuse it later on. But the reference allows you to do less things, like you cannot move the values away. In the case of iter, you cannot mutate them in place and so on. So overall, the answer is we'll get into more of that right in the next chapter. My understanding is that the index checking in Rust is implemented with data ownership. Does this only happen during compilation time, other than any checks during runtime? So unfortunately, index checking is not always implemented at compile time. The reason is basically, imagine you have some array in your code, and then you ask over standard input your user to tell you at which index you should access this array. And now in your code, you want to access the array at this particular index. In this scenario, because the index value comes from the user, the compiler has no way to know in advance which element you will be trying to access. This means that if we want to have general purpose indexing operations that can work with any index, we must sometimes have runtime checks. Now, during optimization passes, the compiler will try to eliminate those runtime checks and turn them into compile time checks. Unfortunately, this particular operation is a bit brittle and it will not always succeed. This is why you're generally better off preferring iteration over direct indexing when maximal performance is desired in Rust. Do we differentiate between lambdas and closures in Rust? No, I use them as synonyms. So for those who would care, so environment capture in Rust can work in two different ways, either by value or by reference. We'll get again more into those notions in the next chapter, but from the Rust perspective, they are the same thing. Like we call them closures, we call them lambdas, we call them anonymous functions, because people come from different programming languages where the same concept is called differently. But to Rust, they are all the same thing. Okay, so a similar question by Matthew. So regarding anonymous functions not capturing their environment, okay, I agree that might be confusing. I've seen the three terminologies all around, and I thought since people already know about functions, maybe calling them anonymous functions would be more familiar. But yeah, if you want to call them closures or lambdas, that's fine by me. To me, it's three different names that different people use for the same thing, depending on which programming language they come from. When we define the plus operator, does it keep left to right precedence? Is it customizable? No. The properties of operators are defined by the language. The only thing we can do is to add new implementations of this operator. But the precedence is, as in mathematics, when mathematics says something and as defined by the language specification otherwise. Can we alias trait, like to have a shorter-hand syntax to designate a complicated trait definition? Not yet, but as people pointed out in the future, we'll be able to in future versions of the language. That's currently available as an unstable feature on nightly compiler versions. Is zipping efficient? Yeah, again, as I mentioned early, zipping is in Rust usually as efficient as iteration over indices in C. You can do zips of zips indefinitely and it will keep working. And again, my understanding is that this is the case because the Rust compiler handles tuples a bit specially to ensure that at the backend level, they will the elements of tuples will remain resident in CPU registers, and the underlying tuple construct will not be materialized on the program stack, an optimization known as scalar replacement of aggregates. Other best practices I, beginner, can refer to when writing Rust. For example, I can feel good about using zip and chain functions in the pipeline. So as someone mentioned, I would say the first best practice would probably be to follow what the standard library does, use standard library abstractions where you can, because that's kind of a common vocabulary that every Rust developer shares. So when you are using those abstractions, people are familiar with what you do and it feels right to them. Obviously, using the standard library is not a complete guideline. Like, for example, it doesn't tell you whether you should use iterators or indexing. I'm not aware of general guidelines for implementations of code. like do this, do not do that. But I know of a few specific guidelines. There is a Rust performance book that goes into some suggestions on how you should write code to get optimal performance. Many of its topics will actually be covered during this course, even if this particular course is more focused on floating point operations, and we'll get a bit more into the details of them. And there are some famous guidelines on what your libraries APIs should look like when you're publishing libraries to other people. So I will put links to both of these resources in the chat. I'm pretty sure there are some others. Like I think I remember a nice blog post about how to keep your how to improve the performance of compiling your Rust programs, but I cannot find it right away on the fly. I don't think I have this one bookmarked. Then we have Nara asking, does the compiler not automatically fuse the multiply and add when defining the reduce as x times y plus accumulator? Why do we need to use mul add operator manually? So this is actually a very, very old debate between compiler authors. For years, GCC would do the optimization that you are mentioning by default, and Clang would not do it in the C and C++ world. And the reason why that is the case is this transformation is actually not numerically stable in the sense that it changes the output of your program. When you do x times y plus accumulator, you will first compute x times y, materialize the associated floating point number. So like we get a 32-bit result, for example, and then you will add to that the accumulator. So you will do a 32-bit addition and get another 32-bit floating point number. And it means you get two accumulated rounding errors. Whereas when you do a fuse multiply add, the whole intent of fuse multiply add at the hardware level is that you do not get rounding for the first multiplication. What this means is that depending on whether the compiler succeeds to apply this optimization or not, the result of your program will change. And that's traditionally something compiler optimizers have shied away from doing. The argument of GCC historically for doing it anyway is that in this particular case, using fuse multiply add should improve precision. And in the opinion of the authors of GCC, optimizations that improve precision are okay, even if they do change the result. However, even that can be debated because, for example, if I compute the expression that is written in the chat, and now you compare it to this expression, you will see that if x times y and z times t are close, the FMA expression will have a much harder time converging towards zero. This highlights the fact that fuse multiply add is a bit of an asymmetric operation, and you should probably not use it in symmetric expressions like the one I highlighted above. Also, as someone pointed out, sometimes this transformation could also violate IEEE standard. But again, yeah, the explanation is again that it changes the results. So Sergey is asking, when we do V1 plus V2 plus V3, those Rust compile it into the first one or the second one. So it compiles it into the later, but you should know that the former actually also compiles into the later without indexing overheads. I'm not sure if that's clear.
Not really.
Okay. So if in C you write this no, sorry, it's about I know there are 3 arrays actually in this expression. So then yeah, it does compile to the first expression. Sorry, I misread what you wrote. It's the former. Is there any exception to zero-cost abstractions? Oh, yes, there are, and you will see a number in this course. Basically, what we call zero-cost abstractions often rely on compiler backends performing all the right optimizations so that the abstractions are removed in the final machine code. And this optimization process can go wrong in many different ways, like functions can fail to be inlined, and this can result in all sorts of disaster. In this chapter that I ended my presentation on today, in this morning, you will also see that what looks like a zero-cost abstraction of summing the elements of an iterator actually is not when you take it from the perspective of summing floating point numbers as quickly as possible. And we'll get a bit into why that is, but in a nutshell, the reason is that, again, compilers do not allow themselves to transform floating point expressions in any way. Do zero-cost abstractions make Rust compiled programs larger, usually larger than C or C++? If you're talking about the final compiled program, it shouldn't, assuming all the right optimizations happened and the zero-cost abstraction like iterators compiled into a loops, for example, as they are supposed to. You may get an increase in the size of debugging information, and this will this can be a problem on disk-constrained machines like embedded systems where you do need debug information sometimes, but you don't want to have big binaries. This will also have another effect, this zero-cost abstraction, which is that usually it will, to some extent, increase compilation overhead because now you will get lots of generic code that is only instantiated at the time where your program calls it. And this, in turn, will mean that the compiler will need to dive through more code when compiling your application, like more generated code. And this can make compilation slower and use more memory. Seems like it is harder to reason about what is really happening on the processor caches in Rust than in C and C++, considering iterator slices and processor optimization vectorizations. This has not been my experience, mainly because in any case, when you write a for loop in C and C++, you already need, in order to reason about performance, to keep in your head all the common transformations that compiler will apply to this indexing loop. Like you need to think, oh, so this loop looks like it's operating over one element of an array at a time, but actually I know that the compiler will turn it into something that's vectorized, that's unrolled. I know that this can happen in this situation, but it will not happen in other situations, like when I sum elements of arrays. Already in C and C++, making the most of your compiler optimizer requires you to get some mental model of what the optimizer is doing. And I do not find that to be much more difficult in Rust with iterator slices than with C and C++ with loops over indices. Hello, can you please tell how Rust is integrated with the CUDA ecosystem? As I mentioned yesterday, GPU programming in Rust right now is a bit in its infancy. We can do basic things like, for example, if you have compiled CUDA library into a shared object, you can call functions of that shared object in Rust. You can also do more advanced things like you can call CUDA API functions. Writing CUDA kernels in Rust right now requires using experimental projects based on nightly compiler features. It's something that I would personally hesitate to put in production. That being said, if you're interested, you can look at this prototype, which has been abandoned for a couple of years, but someone has said that they wanted to get it started again recently. Any clue on the performance of zip in Rust and Haskell? I wonder whether there is any difference in compilation of Rust and Haskell of Lambda functions. So unfortunately, I do not regularly work in Haskell, so I wouldn't be able to tell how well they optimize their particular zip. But if you want to try, I highly invite you to do so. So Antoine, I dig a bit more into what Ilniki asked. What about loop blocking and tiling with Rust iterators? Well, you may remember that back in the array chapters, I mentioned that we have iterators over chunks of arrays and vectors. This means that we can do things like take an array and iterate over sub-slices of it and do something for each sub-slice. We have 2D equivalents of that, 3D equivalent of that when we use multidimensional arrays with the ND array library. And we can use these to implement typical loop blocking and tiling optimizations. Does this answer the question? Okay, perfect. If there are no other questions, then let's get working on this. So Damien, unfortunately, I do not have solutions for the first exercises yet. I have only done it for the Grayscott part, but maybe we can discuss which specific parts you're struggling with, and then I can clarify that hopefully. But yeah, thanks for reminding me that I also need to add those solutions at some point. So concerning how criterion output should be read, so maybe let me give you an example here. I will just run some benchmark on my machine, and once I get some output, I will show you how that's read out. Right now it's compiling. So that's a bit of a big project because It's a project where I tried to implement many different versions of the Gray-Scott simulation that you are going to see later in this course. And because you have all these different versions, you have quite a number of dependencies for both the CPU side, the GPU side. You have quite a few kernels to compile and so on. In any case, so ultimately you get this sort of output. So it tells you which benchmark it's running. I tend to give them some names that are easy to read. And when a benchmark finishes running, you get this sort of output. So how do you read that? First, you know that this particular workload that you have defined as an iteration has on average taken 400 nanoseconds to run, 444.12. And you also get 95% error bars. If you specify that one iteration of the micro benchmark is about processing n bytes of data or computing n operations of a certain type, like computing n pixels of an image, processing n floating point operations, and so on, then Criterion will also translate this number into a throughput number, which in this particular case tells me how many pixels of the simulation I am able to compute per second. So here I see that I'm able to compute 235.24 millions of elements per second, millions of grid cells per second. And again, I have error bars before and after. Finally, I have sometimes this. So this you should see as a warning that your machine is under load. That's obviously my case. I mean, right now I'm running a Zoom call with you and chatting about all sorts of things. So yes, my CPU is busy with some other things that running the benchmark. Thankfully, Criterion is relatively clever as far as software is concerned. And it does some statistical analysis like bootstrap sampling and other outlier criteria to detect which measurements seem very different from the others and eliminate them. And at the end, it tells you, okay, well, I have some that are a bit away from the overall distribution, some that are more away, some that are completely weird. And then if you have several benchmarks, it will just keep on running all of them one by one. And you will see that for this particular benchmark, as I keep running it for larger and larger images, throughput improves, which is a kind of a general result anytime you have some kind of loop. Usually CPUs have a bit of a warm-up period where they are less efficient, and then after enough iterations, they start becoming more efficient, and so your average throughput increases. Until at some point, throughputs are decreasing, and this is linked to the fact that we are getting out of the CPU caches, and the program that used to be compute bound now becomes memory bound. But anyway, that's getting beyond what Criterion does. I hope that answers your question. And yeah, for the first question, yep. Sorry about, I only wrote the solution for the later exercises, not the earlier ones, because I was a bit in a rush in the last school and I forgot to go over that again. So if you have specific questions, please ask them and I'll get through them. Okay. So the question about assertions, I answered in writing because I was not sure it would be of your interest, but basically you do not in Rust disable assertion via compilation flag. You disable them locally on the call site. So about the problem with std-scmd not being able to use some ELP yet. So the issue here is that to implement the instruction level parallelism based version of sum, I need to use some traits from the crate from the ecosystem called num traits. And this crate from the ecosystem does not have support for nightly only types like the std-cindy types. So as a result, if you try to call some ILP for an std-cindy type, you will get an error about the numtrace type not being implemented for this particular type. I'm not sure if this fully answers your question, otherwise I can get into a bit more details. Yes, that's about 1 and 0, basically. I need a neutral element in order to compute a sum, because that's how I initialize my accumulator. And same for products. I need a neutral element of multiplication, which is 1. I take that as a sign that probably that was a good enough explanation. Gregor, it's okay. So the way you interpret the results from the benchmark is basically my intent here was to show you how bad the performance of a naive sum that just calls the iterator sum method is when you're manipulating floating point data. And the way I propose to do that is by having you thinking about orders of magnitude. So let's assume that your CPU has a frequency of 2 gigahertz. That's common for HPC centers. Usually client-side CPUs can clock a little bit higher. We know that, let me share my window here. Make it bigger. So we know that with AVX, it is possible to sum 8 single precision floating point numbers per instruction. And we know, well, at least we can find in the literature that our CPU can perform 2 sums per cycle, typically, 2 AVX sums. Then we know that we can sum 16 floating point numbers per cycle. We have 2 billion cycles per second. So we should be around 32 billion floating point sums per second. If we are much less than that, it means that something's wrong. You can get a more precise estimate of your CPU's clock rate in various ways. First, on Linux and macOS, LSCPU can tell you what is the min and max frequency of your CPU. That's already a better indication. Usually, if you have only a single thread running, you are closer to the max than to the min. But sometimes data center CPUs are clocked voluntarily at the min in order to improve the reproducibility of execution times. And if you want a measurement of your CPU clock frequency at the time where the job is running, then you will need to use more advanced tools like PerStat on Linux and event tracing for Windows and Windows. I think on macOS, Xcode also provides something similar. Does that answer the question? I will assume it does. So let me explain this again more slowly then. We have a CPU that can run through 2 billion clock cycles per second. Each of these cycles, it is able typically to do 2 vectorized sums. So we know that it's able to do 4 billion vectorized sums per second by taking the product of these two numbers. Then our typical CPU again has AVX vectorization. And if we use that correctly, then we should be able to get to sum 8 floating point numbers with each other anytime we compute a vectorized sum. So by multiplying that with the previous results, we get to the conclusion that CPU that supports AVX with two-way instruction parallelism and 2 gigahertz clock rate should be able to compute 2 by 2 by 8, which is 32 billion floating point operations per second. So no, that's not, the factor of 2 is not 64 divided by 32. So to get this one, you will need to have access to some microarchitectural information that one of the best resources for this I find is a website called Wikitchip. Unfortunately, it's not kept up perfectly up to date for newer CPUs, but you can get slightly older CPUs like Skylake from Intel, and it has not changed that much since that time. So let me show you what that looks like. So if you go to there, assuming you have an Intel CPU with a Skylake architecture or a slightly more recent architecture, it doesn't matter. Yes. When you look inside of a CPU core, you have a nice big machinery that looks a bit like this. So on the top, you have something called the front end, whose job is to get some instructions from memory and schedule them for execution. Basically, it reads the machine code and translates that into some representation that the CPU can directly work into, and it does a couple of optimizations along the way. And once you've passed that, you reach another part, which is the backend, where the magic happens. So modern CPUs are superscalar, which means that on the backend side, they can be executing at any given point in time multiple instructions per cycle. So here, if we look, we will see that we have floating point FMA, and here you need a bit of more context to know that sum is implemented via FMA on modern Intel CPU. And you see that on port 1, we also have a floating point FMA. And if you look at the other execution ports, you see that they are unable to execute floating point FMAs or sums. This means that modern Intel CPU, actually a CPU from the Skylake era, is able to, at most, run 2 vectorized floating point sums per clock cycle. This is why I give you this number. It's a bit involved to compute it. And yes, as discussed by Nara in the reply of your answer, when you are looking at CPUs at this level, it's good to keep in mind that there are 2 different characteristics of CPUs when it comes to instruction execution. There is latency and there is throughput. What I've been talking about so far is throughput. Throughput is assuming you get a constant stream of instructions coming how many instructions can you execute every clock cycle in the steady state. Latency looks like something a bit different. It looks at the time that elapses from the moment where the CPU schedules an operation, like an addition, and the moment where you get the result of that operation. And more often than not, it actually takes multiple clock cycles for the result of an instruction to come out. And this is important because it means that in order to saturate your CPU's resources, you will need to have more instructions than just your the number of ALUs you have, because you also need extra instructions so that you can start scheduling those while waiting for the output of the previous instructions. I'm not sure if that makes sense. Perfect. Don't hesitate if you have any other of these architectural questions. Originally, this course was run in the context of a school where I had a full presentation on CPU architecture, and I detailed this sort of phenomena a lot more. So I expect the explanations to be a bit on the light side because of this, as I didn't want to duplicate that particular course at the time. I'm not sure if I translated that course to English yet. I plan to do it for the next edition to the school next year. Let me check if I already have an English version somewhere. Otherwise, as far as I know, these days Google Translate can translate PDFs, so maybe you could try running that through Google Translate and see how good the output is. Yeah, it's in French. So where is it? It's there. So I put the link in the chat, but actually I can just put it on the Q&A as well. So in order to see the throughput, so what you have to do is to tell Criterion how many operations you are doing in one iteration of the benchmark. This is done using an API called benchmark groups. So I will just share an example of a pre-existing Criterion benchmark I have that does this. It will be easier to follow. Let me look for one real quick. Okay. So so far in the course, I've been showing you the basic API of Criterion, which is called bench function. You just take the criterion object that you get from criterion, and you call bench function on it, and you specify the benchmark name, what an iteration looks like, and then criterion does its thing. For more advanced scenario, criterion allows you to create benchmark groups which add one level of hierarchy to your benchmarks. The idea is that you give the group a name, and then inside of a group, you can put any number of benchmarks, and this allows you to compare the throughput of these different benchmarks inside of the group. For reasons known to the criterion developer alone, you need to use this benchmark group API in order to access then one throughput method of the benchmark group object, to which you can then pass an enumerated type, which has several variants. Here we are using the elements variant. And then I use that to say, okay, I am computing that many elements for that number of compute steps. And then I use the bench function method of the group, not the original criterion object. And this will result in a benchmark that has throughput measurements. Does that answer the question well enough? I will take silence as a yes. So Gregor was asking, what is our goal now? So, as usual, the goal is to move forward, obviously. The idea is that you should progress through the chapters at the pace where you feel like you are understanding what you're doing. But at some point, I will have to move forward a bit because I want to show you not just what Rust looks like on small computations, but also what it looks like on larger, more realistic computations. And for that, I will need to use the Gray-Scott simulation. What I would actually propose is that we do a little break, 20 minutes break. And then I go through the remaining chapters, doing the explanations orally as I've done so far. And finally, once that's done, I will explain a bit the Gray-Scott problem. And at this point, I would advise that you switch to working on this problem, even if it means that you will need to get back to the smaller compute exercises later on to get a full understanding on them. So if that's fine for everyone, I will grab my cup and I will see you in about 20 minutes, so around 14, so about 2:55 p.m. or something like that.